Hello everyone. Today we will discuss chapter 7 or chapter 13 in the textbook. The title is Reacting Mixtures and Combustion. This is the learning outcomes of this chapter. First is to define complete or stoichiometric combustion, theoretical air or stoichiometric air, and then enthalpy of formation and adiabatic flame temperature, and compute values associated with each term, and then to develop a balanced reaction equations for combustion of hydrocarbon fuels. So there will be some topic that will review what you have learned in the chemistry class. Next one is to apply mesh energy and entropy balance to closed system and control volumes involving chemical reactions. This is the topic that we will discuss in this chapter 7. So the main focus will be on the combustion, including the introduction of the combustion itself, and then how do we apply the conservation of mass and energy on this reacting system, and then to determine the adiabatic flame temperature. And then there are several topics that are crossed out here, so it means we won't discuss this topic, but there are a couple topics that is interesting and is a hot topic because they are under research and development right now. For example, fuel cell. So when people talk about other option of the energy resource, fuel cell is one of the option, and there is a subtopic in the textbook. So I encourage you to have a look what does means with this fuel cell and how does it work and so on. Okay, let's take a look on the combustion fundamentals. Let's review about the chemical reaction, and I believe you got this introduction in the chemistry, the first year of the bachelor degree. So when a chemical reaction occurs, the bonds within molecules of the reactants are broken and atoms and electrons rearrange to form products. So this is the schematic of a reaction. So on the left side we have reactants and then doing a chemical process. So the species or molecules in the reactants reacts and then they produce products here. So we have reactant on the left side and then products on the right side. And the molecules or the compound in the reactants are not necessarily the same as the one in the products. Combustion reaction is one type of the chemical reaction. So in combustion reaction, rapid oxidation of combustible elements of the fuel results in energy release as combustion products are formed. So this is the schematic of the combustion reaction. On the left side, as the reactant, we have a fuel, and then the fuel needs an oxidizer to be burned to produce the product. In the product, usually we have CO2 and then water vapor and so on. And currently, there are three major combustible elements in common fuels. One is carbon itself, and then hydrogens, and number three is sulfur. So depending on where do we get the gasoline, diesel or natural gas, this fuel might contain sulfur, and this sulfur can be oxidized to form, for example, SO2. And then combustion is complete when all carbons present in the fuel is burned to carbon dioxide, and then all hydrogen present is burned to water, H2O, and then all sulfur present is burned to sulfur dioxide, SO2, and then all other combustible elements are fully oxidized. So when these conditions are not fulfilled, then we have a case that the combustion is incomplete. There are several types of the fuels available right now in the market, And we can differentiate this fuel according to the type or class of the fuel. So the first class of this fuel, it's called alkyl compound. Under this alkyl compound, we have paraffin. So with the formula of CnH2 plus 2, for example, we have methane as the main source of the natural gas, and then we have octane, so C818, so it falls under this paraffin. And then we have napthanes or cycloparaffin, and then on this one we have olefins with the formula of CnH2n. An example of this olefin is acetylene, so C2H2. The next class is called aromatics. So it has a ring structure as shown in this figure, and the formula for the CnH is CnH2n minus 6. Example of this aromatic is benzene. And then the last fuel class here is alcohols. So this is the formula. So CnH2n plus 1 OH. Example of this alcohol is methanol. Okay, so CH3OH. And then we have ethanol. So this is C2. So ethanol is one of the popular additive for gasoline. So you can find in almost any fuel station. So when you fill in your car fuel, take a look on the reading. Usually you see one statement or one sentence there that this fuel contains maximum 15% of ethanol. So, and then sometimes you can see like E10 and then E15. So E15 means that the gasoline has been blended with a 15% ethanol. It means the gasoline contains 15% of ethanol, and this ethanol might be one of our future energy because it is one of the renewable energy. So ethanol can be produced from corn or sugarcane and so on. Let's take a look on this example. Determine the balance reaction equation for complete or stoichiometric combustion of methane, CH4, with oxygen, O2. For complete combustion, the product contains only carbon dioxide and water. So we have CH4 and O2 on the reactant side, so on the left side of the arrow sign. So this is the reactant, and then on the right side the product are CO2 and H2O, and then here we have a coefficient of A, B, C that denotes the moles of O2, and then B is for CO2 and C is H2O, and then this is per mole of CH4 because we only have 1 mole of this fuel, so methane. So to determine the coefficient of A, B, and C, we need to apply a conservation of mass to carbon, hydrogen, and oxygen. So we can start by looking at the carbon mass conservation, so C. So on the left side, on the reactant, we have 1 C. So on the right side, we must have 1 C as well. So it means B must be 1. Okay. And then we equalize the number of atom H. So on the left side, we have 4 atom H, and then on the right side, so it means C must be 2. So we have C equal to 2. And then the last one is to equalize the number of atom O. So on the left side we have 2A, and then on the right side we have 2B plus C. So we got B from the conservation of carbon. So B equal to 1. Therefore C equals to 2 here. Okay. So once we completed this A, B, and C, then we can rewrite the reaction by inserting the value of A, B, and C, so that we have this complete reaction. So this is a stoichiometric reaction of methane with oxygen as the oxidizer. So we have 1 mole of methane plus 2 mole of oxygen, and the product is 1 mole of CO2 plus 2 moles of water vapor. Next one is hydrogen. So hydrogen is straightforward. So this is the stoichiometric or complete reaction of hydrogens. So we have a fuel as H2, and then oxidizer is oxygen, and then the product is only one compound here. This is H2O. So for a stoichiometric or complete combustion, we have 1 mole or 1 kilomole of hydrogen. It's required half kilomole of oxygen, and the product is 1 kilomole of water. And then if we multiply the number of mole by the molecular weight of the corresponding species, then we have here 2 kilogram of hydrogen plus 16 kilogram of oxygen, and the product is 18 kilogram of water. So if you look at on this reaction equation, the number of moles for the reactant is not necessarily the same as the number of mole for the product, but the mass between the reactant and the product must be the same. Therefore, it fulfills the conservation of mass here. Oxygen is required in every combustion reaction, so that's clear. So in most combustion application, usually air provides the needed oxygen. So why? Because if you want just to get a pure oxygen, then you need to pay it. So it's not free, but air is free. So when we use air as the oxidizer of the fuel combustion, usually we apply this simplification, and this is for a dry air. So dry air means that the air doesn't contain any water vapor, so it's just air, and this air can contain oxygen, nitrogen, CO2, argon, and so on. So when we use dry air as the oxidizer for the fuel combustion, we use or we apply this simplification. One is all components of dry air other than oxygen are lumped together with nitrogen. So in here we ignore the amount of CO2, we ignore the amount of argon, we ignore the amount of any other species inside the dry air. So we only have oxygen, and then the rest will be nitrogen. So with this idealization, air is considered to be 21%. So here 21% of O2 and 79% of nitrogen on molar basis. So on mass basis, then you will have different composition. Okay. So accordingly, when air supplies the oxygen in a combustion reaction, every mole of oxygen is accompanied by 3.76 moles of nitrogen. So this comes from 0.79 over 0.21. So once again, when we use air as the oxidizer of the fuel, in this class, we will assume that air consists of 1 mole of O2 and 3.76 mole of nitrogen. And then the nitrogen present in the air is assumed inert, except when we have a very high temperature. So we have more explanation in the next slide. So nitrogen present in the air is assumed inert. And then the molecular weight of dry air, so we have used this number quite a lot previously. So the molecular weight of dry air is 28.97 kilogram per kilomole or gram per gram mole. When moist air is used in combustion, the water vapor present in the air should be considered in writing the combustion equation. So depending on the statement whether we use dry air or moist air, so you might need to include water vapor, or you might need to exclude water vapor in the air. This is for nitrogen. So nitrogen undergoes a change of state if a high enough product temperature is attained. So nitrogen can form compounds such as nitric oxide, so NO, and nitrogen dioxide, NO2. And these two compounds are a source of NOx emission. So even trace amount of oxides of nitrogen appearing in the exhaust of internal combustion engines can be source of air pollution. So NOx, this is one of the emission that is dangerous, and every country apply a strict rule to minimize this NOx emission. Next one is air-fuel ratio. So the air-fuel ratio is the ratio of the amount of air in combustion reaction to the amount of fuel. So this is a straightforward definition. So air-fuel ratio is the ratio of the amount of air in a combustion reaction to the amount of fuel. So the air-fuel ratio can be written on a molar basis. So it's mean here we have AF with the upper bar, so this is on molar basis. So this is the ratio of the number of moles for air to the number of moles for fuel. And then on mass basis, so we have AF here. This is the ratio of mass of air to the mass of fuel. And then if you want to apply a conversion between mass basis and molar basis for this air-fuel ratio, we can use equation 13.2. So AF on mass basis equal to AF on molar basis times the molecular weight of air, 28.97, over the molecular weight of the fuel. So depending on the fuel type, if it is methane, CH4, then it will be around 16. Okay, if it is gasoline and can be represented by octane, so CH818, so the molecular weight will be 12 times H plus 18 times 1. Okay. So the fuel-air ratio is the reciprocal of the air-fuel ratio. So we have AF, and then we can also have FA, so fuel-air ratio. So this is the FA is the reciprocal of the air-fuel ratio. Let's take a look on the theoretical or stoichiometric amount of air. The theoretical or the stoichiometric amount of air is the minimum amount of air that supplies sufficient oxygen for the complete combustion or for the stoichiometric combustion of all the carbon, hydrogen, and sulfur present in the fuel. So for a stoichiometric or complete combustion with the theoretical amount of air, the product consists of CO2 and then H2O and SO2 plus nitrogen present in the reactant. So we don't have O2 in the product, we don't have CO in the product. So it's only CO2, H2O, SO2 if the fuel contains sulfur, plus nitrogen present in the reactants. Okay, so normally the amount of air supplied is either greater than or less than the theoretical amount. So I just take this statement from the book, which is might be correct, might be not, because there are several engine technology that apply a complete or stoichiometric combustion. So it's mean the amount of the oxygen is just sufficient to have a complete combustion. So, but yes, there is other technology that apply higher oxygen or higher air. So it's mean we have more than sufficient air needed by the fuel, and if we want to have a higher power, so we need to increase the amount of fuel. So it's mean the amount of air is less than it's needed for this complete combustion. So it's mean it is less than the theoretical amount. So the amount of air actually supplied is commonly expressed as one we use here, a percent of theoretical air For example, if we say, okay, we burn this methane with 150% of theoretical air, so it's mean the amount of air is 1.5 times the theoretical or the stoichiometric amount. The second parameter, this is similar but just different name. It's called a percent excess or a percent deficiency, so of air. For example, if we say 50% excess air, this equals 150% of the theoretical air. Or if we say 50% deficient air equals to 50% of the theoretical air. So the third parameter that is used to represent the amount of air, what is called equivalent ratio. So this is the most popular parameter used in internal combustion engine combustion. So the equivalent ratio is the ratio of the actual fuel-air ratio to the fuel-air ratio for a stoichiometric or complete combustion with the theoretical amount of air. So the reactant is said to form a lean mixture when the equivalent ratio is less than 1. Equivalent ratio less than 1, it means we have the air amount that is higher than the stoichiometric or theoretical amount of air. And then when the ratio is greater than unity, the reactant is said to form a rich mixture. So in this case, we have more fuel. It's also mean in here we have less amount of air than the amount for a stoichiometric combustion. So leans, it's mean we have less fuel. Maybe it's an easy way to get a good memory of this definition. So once again, leans mean we have less fuel, and then rich we have more fuel. Let's explore the combustion concepts. The balanced chemical equation for complete combustion of methane with theoretical amount of air or with stoichiometric amount of air can be seen in this equation 13.4. So to have a stoichiometric combustion of methane, so you know methane is the primary compound or species for natural gas. So to have a stoichiometric combustion of methane, you can see in this equation it required 2 mole of air, okay? And on the right side, the product has 1 mole of CO2 and then 2 moles of water vapor and then 7.52 moles of nitrogen. So the coefficient 2 before the term of air here, O2 plus 3.76 N2. So we just talk about this one. So the coefficient 2 is the number of moles of oxygen in the combustion air per mole of fuel. So you have 1 mole of methane here. And then the number of moles of nitrogen in the combustion air per moles of the fuel is 2 times 3.76. Okay, 2 times 3.76. And then the amount of combustion air per moles of fuel is the sum of the mole of oxygen, which is 2 mole, plus the moles of the nitrogen. So 2 times 3.76. So this is the amount of combustion air mole per mole of fuel. So per mole of fuel, we have 9.52 moles of combustion air. So, and then the air-fuel ratio on molar basis is the ratio between the number of moles for air. So in this case, we have 9.52 over the number of moles for methane, 1. So AFR, so usually people use AF or AFR. So let's use AF here. So AF equal to 9.52. So this is on a molar basis. What happened with the air-fuel ratio if we add more air in this methane combustion? Your intuitive thinking will say that the air-fuel ratio will increase. So let's say we want to burn this methane fuel with 150% theoretical air. 150% theoretical air. So if you look at on this reaction equation, we have 1 mole of CH4, and because we want to add 50% more of air, so you can see in here we put 1.5 ahead of this stoichiometric mole number of air. So it's mean here we once again we add 50% more of air in this methane combustion. And then on the right side we have CO2, and then we have H2O, and because we have more air, so you will expect having a residual of oxygen. So it's mean not all oxygen is used to burn this methane. So in the product you will have oxygen here, okay, and then you also have nitrogen here. So the amount of air per mole of fuel is 1.5 times the theoretical amount or the stoichiometric amounts determined by equation 13.4 in the previous slide. And then the excess air supplied appears in the product as O2. Okay, it makes sense because you have more oxygen. So it's mean in the product you still have some oxygen that doesn't take part in the reaction at all. So and as a greater amount of nitrogen than equation 13.4. So it makes sense because on the left side you have 50% more of nitrogen. So on the right side you also have 50% more of nitrogen compared to the case for the stoichiometric or complete combustion in equation 13.4. So the air-fuel ratio on a molar basis, in this case you have for a 150% theoretical air is 14.28 to 1. So it's mean you just multiplied whatever you get from the previous slide for the stoichiometric combustion with this one, 1.5. So it's mean here you burn this methane with 150% stoichiometric or theoretical air. Let's take a look at this example. So this is example 13.1 in the textbooks. Determine the air-fuel ratio on both a molar and mass basis for the complete combustion of octane. So octane is CH818. So usually this octane is used to represent the behavior of gasoline. So we need to determine this air-fuel ratio on molar and mass basis with A here, the theoretical amount of air, so it means stoichiometric or complete combustion, and then B is with 150% theoretical air or 50% excess air. Let's take a look on the solution of this problem. So this is the reaction equation for octane, so CH818. So it's a react with air, dry air, consisting of 1 mole of oxygen and 3.76 mole of nitrogen. And then in the product, we have CO2 and then H2O and N2. So in this case, the reaction here represents the stoichiometric or complete combustion. So the product only have CO2, H2O, and N2. And then by applying the conservation of mass for the carbon and then hydrogen, oxygen, and nitrogen, we should be able to get the number for A, B, C, and D. So there are 4 equations with 4 variables. So we should be able to fix this number. So from the conservation of C, on the left side we have 8C, on the right side then we need to have B equal to 8. And then from conservation of H, we get C equal to 9, and then we can get B from, we can get A from this O conservation. So A here equals to 12.5. And then once we got A, then we can calculate D. So D is 3.76 times A. So D equals to 47. And then once we fix all coefficient in this reaction, then we can put the number and we get this stoichiometric reaction for octane. So for a complete or stoichiometric combustion of this octane, we need to have 12.5 moles of air. Okay, and then on the product we have 8 mole of CO2, 9 mole of H2O, and 47 moles of N2. And then the air-fuel ratio on a molar basis is the ratio between the total number of moles of air. So air here we have 12.5 O here plus 12.5 times 3.76, okay, and then divided by 1. 1 here is the number of mole for octane. So the air-fuel ratio for octane on a molar basis is 59.5 kilomole air per kilomole fuel. And then on mass basis, we just need to multiply the air-fuel ratio on a molar basis by the molecular weight of air, 28.97, divided by the molecular weight of octane, so 114.22. Okay, so we got this air-fuel ratio on a mass basis for octane is 15.1. So it's mean to have a complete or stoichiometric combustion of octane. So for 1 kilogram of fuel required 15.1 kilogram of air. Okay, next question. What's happened with 150% theoretical air? So it's mean we have 50% excess air here. So in the equation, you can see in here, we put 1.5 ahead of the mole number for stoichiometric combustion here. Okay, so same thing, you need to apply the conservation of C, H, O, and N to get the value for A, B, C, and D. So it should be simple here. And then once you get the number, you just plug into the reaction. So you have this reaction to represent the combustion of octane with a 150% theoretical air. Okay, so in this case, we need 18.78 moles of dry air, okay, to combust 1 mole of octane. So the air-fuel ratio with this 150% theoretical air is 89.25. So this is the same as 1.5 times the stoichiometric air-fuel ratio from the previous slide. And then on a mass basis, we have this one, 22.6 kilogram air per kilogram fuel. Next one is dry product analysis. In practical application, combustion is generally incomplete. So it is difficult to have a complete combustion. So it means it is difficult to combust completely methane with air, and then in the product we only have a CO2, H2O, and nitrogen. So in most of the time you will see some of the unburned fuel. You will see some of the oxygen in the product. So this incomplete combustion is related to, for example, the introduction of the fuel. And then how can we design a combustor that can guarantee that each molecule of the oxygen can react with the molecule of fuel following the stoichiometric combustion. So it is not easy. Okay. So the product of combustion of actual combustion processes and their relative amount can be determined only by measurement. So I don't know, there is a class, it's called measurement system, whether it will cover one of the measurement method for this combustion product. So at Southwest Research Institute, we have several types of the measurement tools for this combustion product quantification. One of this is it's called gas chromatograph that can measure the amount of CO2 and so on. So certain devices for measuring the composition of combustion product report the analysis on a dry product analysis basis, where the amount of the mole fraction are given for all products except water. So it's mean it report the mole fraction of CO2, water vapor, maybe urban fuel without water. So it's mean it has a water in the actual product, but the report doesn't contain the water. So if we want to get the report in actual basis, which is called sometimes it's a wet basis, then we need to consider the amount of water. So dry product analysis here means that the report of the combustion product excludes the amount of water. Let's take a look on this example to have a good understanding of this product analysis. So we have ethanol here. So ethanol, so it's C2H5OH. It's burned with air to give products with a dry molar analysis 3.16% CO2, 16.6% CO, and 80.24% nitrogen, and then determine the balanced chemical reaction. So in this case, for convenience, let's use or let's base this solution on 100 moles of dry product, and then we can have the reaction shown in this slide. So in this case, we have 80.24% nitrogen, or we can say we have 80.24 mole of nitrogen in the product, and then 16.6 mole CO and 3.16 mole of CO2. Okay, and on the reactant we have for sure ethanol. Okay, it's react with air consisting of 1 mole of O2 and 3.76 mole of N2. And then see here we need also to add this term, okay, to account for the water formed in the reaction. Okay, so we need to include this one. And then let's say we put A here that denotes the mole of fuel required for 100 moles of dry product. Okay, so this is the dry product. So we have 100 mole of dry product, and to have this 100 mole of the dry product, we need to have a mole of ethanol here. Okay, and then it will require a B mole of air, and the water vapor produced in this product is C mole. Okay, so the task is to determine what is the value of A, B, and C here. Okay, so we have this equation, and then we need to apply the conservation of mass for C, H, N, and maybe O. Okay, because we only have 3 variables, we can just pick up 3 conservation of mass here. Let's take carbon, and then hydrogen and nitrogen. Okay, for carbon on the left side we have 2A. Okay, on the right side we have 3.16. okay, plus this one 16.6. so we get A here equals to 9.88, and then by applying the conservation of H, we get this correlation. So we got A already here, so we get C equals to 29.64. And then for N on the left side we have 3.76B. On the right side we have 80.24. So B equals to 21.34. And if you want to check that your calculation is correct, you can apply the balance for oxygen just to make sure. So on the left side we have A plus 2B. On the right side we have 3.16 times 2, let's say here, okay, 3.16 times 2. This is from CO2, and this one is from CO, and this one is from H2O. And then you can check if both result left equals to right, then your calculated ABC from the balance of C, H, and N are true. Okay, so this is the balance reaction along with the coefficient there, and then we can express this equation per mole of the fuel basis. So in this case, you divide its coefficient here with the number of mole of the fuel, so 9.88, so that you get this correlation. So in this case, for 1 mole of the fuel, it required 2.16 mole of dry air to produce this one, this dry product composition. Let's take a look on this example. Methane, so CH4, is burned with dry air. The molar analysis of the product on a dry basis is CO2 9.7%, and then CO is 0.5%, O2 2.95%, and nitrogen is 86.85%. Determine A is the air-fuel ratio on both a molar and a mass basis, and then B is the percent theoretical air. C is the dew point temperature of the product in Fahrenheit if the product are cools at 1 atmosphere. D is the amount of water vapor present in a pound mole per pound mole of fuel consumed if the products are cool to 90 degrees Fahrenheit at 1 atmosphere. So the last two questions here is interesting. So we need to estimate the dew point along with maybe the amount of condensed water here. So methane is burned here with dry air, and then the dry product analysis composition is given, and then we need to determine the air-fuel ratio on molar and mass basis, and then another question is the dew temperature, and the last one is the amount of the water vapor. So this is the reaction for methane, and this is from the given problem. So this is in the statement of the problem. So 9.7% CO2, and then for convenience we assume CO2 is 9 with 9.7 moles, and then CO is 0.5 moles, and then O2 is 2.95 mole, and the rest is nitrogen. On the left side we have CH4. It has a coefficient of A that we need to calculate, and then B here for the dry air, and then C here is the mole number for the water. Okay, and then by applying the conservation of mass for C, H, and O, we can calculate the coefficient of A, B, and C. Okay, and this is the result. Okay, and then we plug in the number to this reaction, and then we can calculate the air-fuel ratio on a molar basis. So this is the number of moles of oxygen plus the number of moles for nitrogen. So 23.1 plus 23.1 times 3.76, or this one. So you can see here. And then this is the number of moles for methane. So air-fuel ratio on a molar basis is 10.78 pound moles air per pound mole fuel. And then on a mass basis, you need to multiply it with the molecular weight of air divided by the molecular weight of methane. So 28.97 for air here and 16.04 for methane. So we got this one, 19.47 pound mass of air over pound mass of fuel. Okay, the next one is what is the percent theoretical air. So in this case, we need to write it down the reaction for the combustion of the stoichiometric condition. So it's complete combustion or stoichiometric combustion. So for a complete or stoichiometric combustion of methane, we have this equation. So it's mean for 1 mole of methane, we will have 2 mole of dry air. So in this case, we can calculate that the air-fuel ratio of this complete combustion for methane is the ratio of the number of mole for dry air. So 2 times 4.76. So 4.76 here comes from 1 mole of oxygen plus 3.76 mole of nitrogen. And we have 1 mole of methane. So you can see in here the air-fuel ratio on a molar basis for the complete combustion of methane is 9.52. And then to get the percent of theoretical air, you just divide the actual air-fuel ratio from the answer of A divided by this stoichiometric air-fuel ratio or theoretical air-fuel ratio. So 10.58 over 9.52, so you get 1.13. So it's mean we have 113% theoretical air or 13% excess air. The next question is the dew point temperature. So in this case, we will use the methodology we learned in chapter 6, okay, or chapter 12 in the textbooks. So to determine the dew point temperature, so we need to get the partial pressure of the water vapor. To get the partial pressure of the water vapor, we need to know the mole fraction of the water vapor and the mixture pressure. The mixture pressure is given in the problem statement. It is 1 atmosphere. So we need to calculate what is the mole fraction of water vapor. So in the product, we have, okay, we use this equation. So this is coming from answer of A. So where we have 13% of theoretical air. So in the product, you can see in here, we have this composition. So it's mean we have 100 mole of the dry composition. So on this one only we have 100 mole, and then we have 20.4 moles of water vapor. Okay, so to get the mole fraction of water vapor, it is straightforward. So it is the ratio of the water vapor mole, which is 20.4, over the total number of the combustion product mole. So this is 100 plus 20.4. So we have 0.169. So this is the mole fraction of the water vapor. So if we multiply it by P, which is 1 atmosphere, then we will get a PV of 0.169 atmosphere. And we need to convert it to PSI because this is, I believe, the unit available in the table. So we have 2.484 psi or pound-force per square inch. And then by doing interpolation in table A2E, we will get the dew point temperature of 134 degree Fahrenheit. Okay, go to the next question. If the product of combustion is cooled at 1 atmosphere to 90 degree Fahrenheit, what will be the amount of water vapor remains? So from C, we know that the dew point is 134 degree Fahrenheit. If we cool to 90 degree Fahrenheit, which is below the dew point temperature, so we will have condensation of the water vapor. So the question is, what is the amount of the water vapor remains in the product? So it's mean the original or the initial amount of water vapor minus the amount of the condensed water. So in this case, we'll still use the methodology in chapter 6 or chapter 12 in the textbooks. So we cool this to 90 degree Fahrenheit, and the saturation pressure at 90 degree Fahrenheit represent the partial pressure of the water vapor. So you will need to use table A to E again to get the saturation pressure at 90 degree Fahrenheit. So open your table A to E, so you will get the saturation pressure of this one, 0.6988 psi. Okay, if we work on basis of 1 mole of the fuel, so it's mean we divide its coefficient in this equation by 10.2 because we want to have only 1 mole of CH4. So in this case, we have 20.4 over 10.2 moles of H2O. So it means we have 2 mole of water. Okay, per 1 mole of CH4, we have 2 mole of water. And then we have 100 over 10.2 moles of dry product, because we have 100 moles of dry product, and the dry product consisting of this one except the water. Okay, and then the mole fraction of the water vapor in the mixture so can be calculated with this one. So on the left side, this is the partial pressure of the water vapor, and this is the mole fraction of the water vapor, because we have n water vapor moles, and then the total number of moles for the gaseous product will be n plus 9.8. So this is from the dry product amount, and this 14.696, this is 1 atmosphere equals to this 14.696 psi. So by solving this equation, we will get n's equal to 0.489, and here is the amount of the water vapor. So initially we have 2 mole of the water vapor, but after we cool it to 90 degrees, we only have 0.489 mole of the water vapor. The rest will condense into the liquid water. Next example, a natural gas has the following molar analysis. So CH4 is 80.62%, and then C2H6, so this is ethane, 5.41%, and then propane 1.87%, and then butane is 1.6%, and nitrogen is 10.5%. The gas is burned with dry air, giving product having a molar analysis on a dry basis. CO2 of 7.8%, carbon monoxide 0.2%, oxygen 7%, and nitrogen 85%. The first question, determine the air-fuel ratio on a molar basis. And B is assuming ideal gas behavior for the fuel mixture, determine the amount of products in kilomole that would be formed from 100 cubic meters of fuel mixture at 300 Kelvin and 1 bar. And the last question is determine the percent of theoretical air. So here we have natural gas with the specified molar analysis. It is burned with dry air, and then this is the engineering model. So each mole of oxygen in the combustion air is accompanied by 3.76 mole of nitrogen, which is inert, and then the fuel can be modeled as an ideal gas. And this is the equation for the reaction. It's pretty long because we have a fuel consisting of CH4 and then ethane, propane, butane, nitrogen. So you can see here, this is the fuel with the given composition. It is burned with dry air. So this is dry air, and the dry product base composition is also given here. So this is also given in the problem. So from this equation, we need to determine what is A here, and then B, and then C. Okay, so you need to apply the conservation of carbon and so on, okay, to get the value of A, B, and C. You can try it yourself. So you will get A of 2.0 892, and then B of 12.931, and then C of 1.93. So please give a try, or you can pick up one of the problem in the textbook which has similar question, just to give you an idea or to help you solving this similar problem in the exam. Okay, so once we fix A, B, and C, we can put in the number in this equation. Okay, so you will get this one, and then you can start calculating the air-fuel ratio on a molar basis. So this is the number of mole for oxygen and nitrogen per mole of fuel. So you have air-fuel ratio on a molar basis of 13.77. And then B, by inspection of the chemical reaction equation, the total amount of product is B plus C. Okay, this is 12.931 plus C is 1.93. It is 14.861 kilomole of product per kilomole of the fuel. Okay, so the amount of fuel in kilomole and F, so this present in 100 cubic meters of fuel mixture. Okay, so and temperature and pressure is given, so 300 Kelvin and 1 bar. You can calculate the number of moles for the fuel from ideal gas equation of state. So pressure is given there, 1 bar, volume is given, temperature is also given. So you will get the total number of moles for the fuel inside this 100 cubic meter is 4.01 kilomole. Okay, and then once you get this one, you can calculate the amount of mole of the products, because the result you get previously is per kilomole of the fuel. So now after we calculate that the total number of fuel moles is 4.01, then you will get the total number of mole of the product is just the multiplication of this 14.86 times 4.01, so you get 59.59 kilomole of the product gas. And then the next one is to calculate the theoretical air amount. So in this case, you need to do a stoichiometric or complete combustion equation for this natural gas composition. So this is the stoichiometric or the complete combustion equation. So the theoretical air-fuel ratio or stoichiometric air-fuel ratio is 9.52. Okay, and then from the previous problem you already got the actual air-fuel ratio. So if you divide the actual air-fuel ratio with this theoretical air-fuel ratio, and then you will get the percent theoretical air. So this is 145% of the theoretical air.